Day 355 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 96, unique binary search trees. The difficulty level is medium, but don't worry because we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, comment, and subscribe. And if you need any new Apple AirPods, go on and check out that link in the description so you can get you some. Now let's see what the question says. Given an integer n, return a number of structurally unique BSTs or binary search trees which have exactly n nodes of unique values from 1 to n. Alright, y'all, that sounds simple enough, but I understand how it can be a little confusing. So let's go ahead and take a look at these examples just to make sure we're doing this problem correctly. So in example 1, we have n equals 3. Before we get to n equals 3, though, so we can understand what's being asked and how it works, let's do an example of n equals 1. If n equals 1, that will mean there would be only one node, which would be the root node, and there would be only one way to create a binary search tree if n equals 1, right? Because it'd be the root node and that'd be it. There would be no other nodes, and that's the only way we can create it. Now let's say n equals 2. So if n equals 2, there would be two different ways we could create or two different binary search trees we could create. We could have one, the root node being 1, and that could point to the right pointer, or the right child could be a 2. We could do it like this, boom, or we could do it like this. Sorry, y'all. We could do it like this. We could add 2, and then we could add the 1 as the left child for the 2. So hold on, let's clean this up. Boom. But these would be the only two trees that we would be able to create, y'all. We wouldn't be able to create any other trees if n equals 2, because of the way binary search trees are set up. The larger nodes have to go on the right side, and the lesser nodes have to go on the left side, right? So these would be the only two ways that the only two subtrees we could create if n equals 2, right? So we would return an output of 2 because there's only two binary search trees that we can create with 2. Whereas if n equals 1, we will return an output of 1 because there's only one binary search tree that we could create. Now let's go ahead and take a look at example 3, where it's going to give us n equals 3, and it gives us all of the different ways that we could create binary search trees with up to 3 nodes, right? So in example 1, we have n equals 3. The output is 5 because when n equals 3, there are 5 different binary search trees that we can create. We could create one like this, boom, or one like this, one like this, one like this, or one like this. But these are the only binary search trees, or excuse me, these are all of the binary search trees that we can create when n equals 3 with up to 3 nodes, right? So, but we don't want to return the binary search trees themselves like we did in question number 95, which is question number 95 is unique binary search trees 2. I don't know why they did it like that, but if you check out yesterday's problem, it was should be question number 95, unique binary search trees 2, where we had to return the actual binary trees themselves. This problem, we just have to return the count of how many binary search trees we can actually create. And in this case, when n equals 3, it's 5, but we don't know what n is going to be. We have to create a solution that will figure it out no matter what n is, right? So that's how the question works in example 1. Let's go and take a look at example 2, where n equals 1. We just went over how it is when n equals 1. There's only one way we can create a binary search tree when n equals 1, and that's with the root node being 1, and there are no other child nodes or anything like that. So there's only one binary search tree we can create, so we return the output of 1. So now that we understand the question, y'all, let's get into the fun part, the actual solution. Solution is not that difficult at all. So The first thing we need to do is we need to create our base case to see if n is equal to 0 or 1. That means there's only one unique binary search tree that can be created, which is either an empty tree or a single node. So we're going to say, to do that, we're going to use a guard statement. We're going to say guard n is greater than 1, else we can open up the brackets and we could just return 1. Boom, just like that. Now we need to create an array to store the number of unique binary search trees for each number of nodes from 0 to n. So for that, we're going to declare a variable. We call it r. We'll set that equal to an array of integers. Boom. Then we're going to open up the parentheses. It's going to be repeating colon 0 comma count colon n plus n plus 1, just like that. Now there's one unique binary search tree with 0 nodes or an empty tree, so we're going to come right here and we're going to just say r square bracket 0 equals 1, and we're going to do the same thing because there's only one unique binary search tree with 1 node, so we're going to say r square bracket 1, we can set that equal to 1 as well. So now we're going to start our for loop, or our dynamic programming table from 2 to n, because we already handled the case of 0 and 1. So for that, we're going to say for I in 2 n, where n is greater than or equal to 2. We're going to open up the brackets. Boom. Now for each number of nodes in I, we're going to try every number j as the root from 0 to I minus 1. So for that, we're going to say for j in 0 ... less than sign I, we're going to open up the brackets. Boom. So now R of j is going to represent the number of binary search trees that can be formed with j nodes in the left subtree, and R of I minus 1 minus j is going to represent the number of binary search trees for the right subtree. So we're going to say R square bracket I plus equals R square bracket j times R square bracket I minus 1 minus j, just like that. And now we can return the result for n nodes. So we're going to come right here and we're just going to say return R square bracket n. Now that should be all she wrote, y'all. Let's go ahead and give it a run. Make sure it runs properly before we submit it. Let's see, and it's accepted, y'all, first try. That's what I'm talking about. Let's go ahead and submit it. Make sure it stays accepted after we submit it. And look at that, y'all. 0 milliseconds beats 100% of users. That's what I'm talking about. Those are some good numbers right there. So with that being said, y'all, I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.